So today we're going to cover section 3.6, and if you haven't yet done so and either flipped over your two-sided paper or flipped to the second page at the bottom, there's actually written work problems on this one as well. So are they written in there or are they not written in there? Somebody help me out. Written in there? So it should say page 215, 16, 23, 28, 31. Is that what it says? Awesome. So 16, 23, 28, 31. There's four. Four written work problems. Let me jot them down. I don't even know. We'll just... It's on some of them and not on others of them. So it may have depended on when you printed your original paperwork, because I may have gone in and making sure that they were there, and then they may have been missing at some point from some of them. So it should be page 215, 16, 23, 28, and 31. So a couple of them are odd, a couple of them are even. You'll turn those in next time, and then you'll have your web assigned work next time. I think it'll be pretty clear once we start this why I want you to do some practice with some written work problems because of the type of problems these are. So let's take a look. What we're going to be covering today is how we can utilize calculus to graph equations. And I am certainly not naive enough to think that you don't have a calculator that you should verify it with, and I encourage you to verify what you're seeing with your calculator to make sure that you don't have any errors in your work. But there's a direct correlation between a lot of the things that we've been doing and a graphical representation of what it represents. Things like concavity, things like increasing and decreasing. They should show up and make sense on a graph if they're going to have any context at all, right? That's what we're doing today, is we're just trying to bridge those pieces and see how they all connect together in terms of a graph. Sound good? The section of material that we'll be covering later on, 3.7, actually we'll talk about applications of how we can then utilize increasing, decreasing, and things like that in more word problem type situations. So we will see applications of that, but right now we want to focus on just the graphical interpretation. So there's basically three different types of things that we're going to be looking for to plot on a graph. So one of them is that we want to make sure that we identify the domain and the range based on the equation that we're dealing with. Sometimes it's all real numbers. It's really easy. It's a polynomial something. If it's a rational function, sometimes we have things that cannot be included, and so we want to look at those. The second thing to determine is intercepts, asymptotes, and any kind of symmetry. Often there's not symmetry, but occasionally there is, and it's sort of valuable to notice that if you've done already the left-hand side of the graph, you get the right-hand side sort of for free. That kind of stuff. Intercepts, you did that back in like college algebra or an algebra course, right, where you're setting things equal to 0 and solving them specifically from the original equations that you were giving, okay? And then asymptotes, same thing. Your denominators are equal to 0 for vertical asymptotes, for horizontal asymptotes. Some of the things we looked at in the limit section will be useful. And then the last piece is the calculus piece specifically, looking at where the graphs are increasing and decreasing, where they're concave up and concave down. And corresponding to those, of course, are maxes and mins and points of inflection, potentially, on all those pieces. So we're going to be putting together a lot of different components that you've learned across the span of the last maybe 5 years at different points in your mathematical background through what we've just most recently done last week, okay? So this is a very synthetic lesson, right? It synthesizes a whole bunch of stuff. All right, so here's an example of one. We're going to do two of them. The first one we're looking at is a rational function. Our function is f of x equals x minus 4 over x cubed. And it actually says to analyze, to sketch a graph, and then to label certain pieces of information. So labeling intercepts, relative extrema, points of inflection, and asymptotes. So I do encourage you, once you have done the calculus parts of that you make sure that your graph that your calculator will produce does look like what you're anticipating that it looks like, because that can help you to catch any mistakes that you've made either in your algebra or in your calculus along the way. So we're going to go through these three steps: the domain and the range, the intercepts, asymptotes, and so forth, and then all the calculus stuff in step 3. So the first thing that we're going to be looking at is the domain and the range. And we're going to be doing that not because it specifically said in the directions state the domain and the range, although it could say that, but because it's going to inform how we make our graph, all right? So in particular, if we're looking at the domain, so there's 3 steps here, the domain, are there any x values that we cannot have in our function? Yeah. Not going to be able to have the value of 0 because of the denominator. 4 is okay. 4 is going to come into something else in a second here. We're going to use the 4, but 4 is okay. So my domain, you can write it in whatever form your WebAssign allows, or whatever you use in my class. It doesn't matter to me specifically. If you're using interval notation, it would look like this. If you wanted to just write down that it's all x not equal to 0 in terms of like a written work, that's fine. I don't care how you write it. WebAssign might push you in one direction or another, but that would be two different options. How about your range? So in particular with a rational function, the range has to do with horizontal asymptotes. Are there any horizontal asymptote pieces that you can't have, or is it potentially, because sometimes it's the case with rational functions that everything's, above a certain value, like everything's on the top half of the graph. It never crosses that horizontal asymptote even. So does anybody looking at this know what the horizontal asymptote is? That's still not what this one is. We're going to come to the 4, I promise. 4 is going to be an intercept. So I alluded to it last time. It's what happens if you take the, I alluded to the horizontal asymptote aspect of this last time. The way we looked at it last time specifically was in limits. What would the limit of this function be as x goes to infinity? It's 0, right? So we would multiply the top and the bottom by 1 over x cubed. That's what you did in section 3.5. And you would find out that you have 0 on top, it goes to 0, and the bottom goes to the value of 1. So we would end up with 0 as our limit. From an algebra perspective, the way that you would have looked at this is by the degrees of the exponents. Okay, so it might have been a little bit since you've thought about it from that perspective, but it works. The degree of the exponent on top is smaller than the degree of the exponent on bottom. And whenever that happens, you have a horizontal asymptote at y equals 0. Okay, so as a reference point, we'll need this in a minute anyway. It's in part 2, so let me actually write that down. We have a horizontal asymptote at y equals 0. We also have the vertical asymptote coming from the domain at x equals 0. But going back to our range then, what does that mean? Well, it means at least on the edges that I don't cross 0, right? I don't cross my x-axis, my line y equals 0. And in fact, in the between there, I might as well. So I'm going to leave the range blank for a moment, and we're going to come back and fill it in once we have just a tiny bit more information in part 2 here to be able to see whether or not it actually crosses that axis, because it might in the middle, or because the limiting behavior in the end and what happens in the middle don't necessarily match up, or whether it really stays away from it. So we'll come back to that in just a second. The other pieces that we are supposed to be doing inside of step 2 are in the intercepts and the symmetry. In particular, the intercepts. So intercepts means when x is equal to 0, what's y? When y is equal to 0, what's x? Well, one of those we can't do. Which one cannot be 0? X. X cannot be 0, right? So if we're trying to sort of find when x is 0, is that your x-intercept or your y-intercept? Do you remember? It's your y-intercept. Okay. So when you're finding your y-intercept, you let x equal 0. And this isn't possible on this one, so there aren't any. So I don't have any y-intercepts on this. Okay, so then let's do our x-intercept. Well, our x-intercept is when y equals 0. And in particular, in order for y to equal 0, if you take a look back up at this equation, in order for this to equal 0, it would mean that the numerator has to equal 0. And then we get x equal 4. There's the one. It's like it's going to come eventually, right? Yeah, so if y is equal to 0, then we actually get x is equal to 4. And that's by setting the numerator equal to 0 specifically. So I do have an x-intercept. I do cross the line y equals 0.
I thought there was an asymptote.
Ooh. So there is an asymptote, but asymptotes only occur when we're talking about horizontal asymptotes, at least in the guarantee at the ends of the graph. They may still cross in the middle, and this one does. So if you want to start with pieces of the graph that we've identified so far, we can do that. So sketch yourself a graph. I've got grid paper. That's kind of cheating, but you can cheat later and get your own grid paper if you wish to. So we have a few pieces of information. We did say that we have asymptotes, at x equals 0 and at y equals 0. That's the axes, okay? I'm going to draw mine in red. I'll shift it over. Okay, so that's one of my asymptotes. And my other asymptote's down here. Okay, so I'm going to cross it in the middle though, because we just mentioned at x equal 4. That's going to be right here. I am crossing my graph. So this is one of the ones that was always tricky, if you remember from an algebra course, to draw, because most of the time when something like this happens, we're trapped with, like, we have things like this going on, like that, or maybe like that, or we maybe have like this, right? They just stay in their own little quadrants and they're nice and neat and tidy. And this is one of the ones that's not, because I actually crossed the axis at 4. Now, the fact that I crossed the axis at 4 and also not say negative 4 means that I don't have any kind of symmetry from the left to the right. Do you see that? I mean, I clearly don't have both sides the same. I also don't have any y-axis or any origin symmetry, which is where you spin it around the origin, right? Because again, that 4 would spin around to being at negative 4. So I don't have any symmetry, so I can write that down as a feature here. There's no symmetry. I promise we'll go back and we'll fill in range in a minute, but we don't really have quite what we need to do so. Our expectation right now might be that it's all of the numbers, and we might be right, but we're going to get a little bit more detailed information before we make that decision. I think we've done everything in steps 1 and 2, except for range. Is that true? I believe so. So we're on to step 3. Step 3 has us doing our derivatives and our second derivatives, okay? So this is not an especially pretty one to do a derivative and a second derivative for, especially the second derivative part. As you may have encountered as you were looking at your homework, there were some messy ones in there, unfortunately. So keep in mind that even if there's something messy on the test, I can't do a whole lot of messy because you don't have a whole lot of time. So it can't all be stuff like that. So rest assured that it will not all be stuff that's messy, right? I promise. Even if there is something on there that is. So let's take a look at finding a derivative then. So the derivative is the denominator times the derivative of the numerator plus the numerator times the derivative of the denominator. Okay, is that okay for the top so far? So over the denominator squared, so x cubed squared would be x to the 6th. Okay. We want to clean up the numerator, trust me. So we have now x cubed. I have, let's see, I have plus 3x cubed. And then minus 12x squared over x to the 6th. So there's some nice things that are going to happen. The first one, of course, is that these combine. That gives me 4x cubed. The other nice thing that happens is that if you compare the numerator to the denominator, everything has an x squared at least in it, right? Yeah. So we can reduce everything by x squared. So I have 4x cubed. Did I miss one?
Shouldn't that be minus in the first derivative?
Yes. My sign should be messed up right there. Moving too quickly. Minus plus. All fixed? Okay, great. So I have negative 2x squared then. I felt like there was not enough signs going on. Here's 12x squared over x to the 6th. And then we can reduce everything by a factor of x squared. So this is negative 2x plus 12 over x to the 4th. That's a far better place to start from than any of the previous steps to doing our second derivative. Okay, is that all right for the first derivative? I'm about to shrink it. Okay, next we're going to do the second derivative from here. So the second derivative will feel much like the first derivative because our function's quite similar actually at this point. So I have the denominator times the derivative of the numerator, minus, we'll get it right this time, the numerator times the derivative of the denominator, divided by the denominator squared. I know we're not done with, we need to use the first derivative still. We haven't done it yet. I just was going to do the calculus parts of it first where we're just making the calculations, okay? All right, so we're going to clean this one up as well. And we probably should expect that it's going to clean up kind of like the last one did because it started out much like the last one started out. So negative 2x to the 4th All right, I'm changing my signs right here. So this is negative. So I now have 8x to the fourth. And then I have negative 48x cubed over x to the eighth. So I have 6x to the fourth minus 48x cubed over x to the eighth. And we can reduce one more time by doing what? Take an x cubed out of every term, right? So I have, let's see, 6x minus 48 over x to the fifth. It's getting a little on the screen. I'm sorry about that. Okay, all good? Okay, so first derivatives and second derivatives give us information. What information does the first derivative, what kinds of information does the first derivative tell us? Increasing, decreasing, and potentially maxes and mins if we decide to do it from there, right? Like with the first derivative test. Okay, so let's go with those pieces of information first. If I set this equal to 0, and I don't need to worry about setting it equal to does not exist. We know what happens when it does not exist. I have an asymptote at x equals 0, right? I mean, I'm going to have that as a value on my sign chart, but it's not going to be a max or a min. I should specify what I'm clarifying there. So as I'm looking at this, I am going to have 0. What else am I going to have? I'll put that in just a second. When will my numerator here equal 0? Close. -6. Yeah, it will be at -6. I'm going to spare the details of writing a whole lot out. But oh, because my sign's wrong when I wrote it over here. That's why. I just transposed it. So I think I've told you guys before, but in case not. So do you see my screen? And I zoom in and I zoom out all the time. That's why I lose signs all the time and numbers, is because I'm constantly zooming in and zooming out. So please keep me on track. If I lose something, say it. That's what's going on. Yes, it is 6. Thank you so much. If I can keep my signs straight. Cool. So we have the does not exist from the denominator at 0. And we have 6. So those are my sign chart values. And we're going to test points in and around those. So maybe you test -1, 1, and 7, or something like that. So we'll test those values. Where do we test them? In the derivative, right. We're going to test them in the derivative. Now take a look down here, and if you look very carefully, you don't have to test them in the whole derivative, because the denominator is always positive. Do you see that? It really is only going to be determined by what happens on the numerator. That's the only piece that's going to have any difference between being a positive denominator. Dividing by a positive won't change my sign. So if I take a look at really just the numerator, it's sufficient. If that bothers you to think about it that way, do it in the whole thing. It's not going to be a problem, but you don't need the whole thing. If I put in -1, what's going to happen? All right, so I'm putting in f prime of -1, and we get a positive. What if I put in f prime of 1? I get a positive. And then what happens when I do 7? Negative. So my signs go positive, positive, negative. What does positive mean? Increasing. Yeah, we'll get to the concavity one in a minute. Not quite. This one's increasing. And then the negative means it's decreasing. So what happens at 6? I have a max. Yeah. So I'm going to have a maximum, and I have absolutely nowhere to write this on my screen, so it's just going to be all over the place at this point. So we are going to have a maximum at 6, what?
Plug it back in.
Plug it back in where? To the original. Good job. All right, so we need to go back to the original equation. 6 minus 4 gives me 2 on top. 6 cubed gives me, what is 6 cubed? 216. What's 2 divided by 216? In fraction form. 1/108, yeah. It's very small, but it's still a maximum. So that actually gives me a piece of information that I can use over here. At 6 and barely a bit above 0, right? That's where that is. I have a maximum point. Now, I can't really plot it at 1 over 108. That's ridiculous. But I can plot it a little bit above the x-axis, right? That's going to be a maximum. So this is very interesting at this point because what I actually have is I have my graph sort of doing this little hill.
One more over.
Oh, yes. Thank you. I have it doing this little hill, right? And I can't even quite draw it really well. Right? I mean, it's doing this. And like we mentioned before, it's got an asymptote down here that's got to be getting close to over here. That's what I know so far. I also know that this graph has to cut through here because it's an intercept. And it's got to keep coming over here close to this, right? So I have basically the right-hand side of the graph looking something like this. So let's check to make sure that what we had said is happening is happening. I haven't written it down yet, but I've drawn it out. It's increasing and then it's increasing again. So the parts that I'm looking at right now actually are these parts surrounding 6. It is increasing and then it is decreasing. So is it in fact increasing from 0 to 6 and decreasing after 6? Yeah, that's what we've drawn in. So I'm going to write it here because I've got space. So it's increasing. So far we've got the 0 to 6. I'll put the other piece in a minute. I'll leave a gap too. And then it's decreasing from 6 to infinity. I know it's increasing over here in the middle spot. Do you know if it's going to be up here or down here? Why, Jewel? Because it's increasing. There's 2 options, and these are them. I mean, I've sketched them both in roughly. And this is the only one of those 2 options that is increasing, right? So I don't have anything drawn well, but the basic graph itself has to be in the top left quadrant. Agreed? It's the only piece between the top left and the bottom left that I actually have an increasing graph. So I do, in fact, have the graph roughly in that top quadrant. So I'm going to write this in here now. I've got from negative infinity to 0 that it's increasing. I need something to have a reference point over there. I need a point. So I don't necessarily care where it is, so make it an easy, nice one to plug in. So what would be an easy, nice number to plug in on the left-hand side of this graph? -1 is the one I was thinking too. If you choose something different, that's okay. But I need a point to plot so that my sketch can have at least a little bit of accuracy to it. I'll get close to the asymptotes otherwise, but I need a point. So if I put in -1 into this equation here, what am I going to get? 5. Does everybody see that? Plug in -1, I get 5. So, am I there? Yep, that's where I am. The same color I was doing before. So my graph has to come down and get close to this asymptote. How do I know it can't cross? Otherwise, I'd have another intercept. You're right. I already had only one intercept, and it was at 4, right? So it's not going to cross again because no other intercept came about as I looked at that piece of the information. And then it's increasing and going further towards the asymptote that's vertical in between. Last piece of information would be our point of inflection and concavities. So over here, again, I set it equal to 0, and I've got it equal to does not exist, but I know that that's at x equals 0. So where will this numerator equal 0? At 8. Yeah? Now it's going to be hard for us to draw that into our graph very well, but this is happening at x equal 8. So in terms of a sign chart, I've got 0 and I've got 8. And we would be testing values in and around them. So I'd test maybe -1, 1, and 9. I don't know, something like that. And again, I can take a look at plugging these numbers into the second derivative, but what do I have to be careful about on my second derivative? Yeah, the denominator is an odd power here. I mentioned earlier because my denominator here was always positive, I could sort of ignore it. Not true for the second derivative. I have an odd power on bottom, which means my denominator can be both positive and negative. So no ignoring this particular denominator because of that. So I need to make sure that as I plug my numbers in, I get positives or negatives. What happens when I plug -1 in? Will I get a positive or a negative? It's a positive, yeah. Positive. What happens when I plug in the number 1? It's negative, and again, we're plugging into the second derivative. And what happens if I plug in the 9? I get a positive. So these are concavity. Up, down, up. That's what that's saying. There's not a point of inflection, though, at 0. What's happening at 0? Asymptote. So don't get carried away and saying, hey, look, it changed to concavity, therefore there's a point of inflection. There was an asymptote there that produced that. But I do have a point of inflection at 8, or at x equals 8 at least, that component of it. So my point of inflection is at 8 something. Go back up to my original graph, or my original equation circled in black there at the top. That'll give me 4 on top. What's 8 cubed? 512? 4 over 512. Say that again for me, Shelby.
Simplifies to 1 over 128.
1 over 128. Okay, so over here, I have 1 over 128 for my point of inflection. And I can write out concavity pieces, right? It's concave up from negative infinity to 0, and it picks back up from 8 to infinity, and it's concave down from 0 to 8. Does that make sense with the graph that you've drawn? Is it in fact concave up from 0 to from negative infinity to 0? Yes. Is it concave down from 0 to 8-ish? It's hard for us to see. We didn't plot it further out. But if we were to be able to zoom in on this thing, what's going on over here is there is this dip up, and it's coming back to look like this. Not quite like that. So that there is, if you will, this is that maximum, and then there's a point of inflection over here at 8. Can you imagine zooming in on this part of the graph and seeing that? I didn't mean to do that way. Yes? That's what's happening there. Okay. We only have 2 minutes left. I am going to do what I did last time, which is I'm going to record it. The second example is much, much shorter. It's way easier to do because it's not a rational function. There's less going on. Okay? So I'm going to push pause. I'm going to let you guys leave, and I'm going to record the next, it's probably 5 or 7 minutes, something like that. You'll be able to watch that last part of the video once it's posted, and you can go in there and do that. And then that way you'll be able to finish the homework for it. Okay? All right, welcome back. We're going to take a look at problem number 2. As promised, it's going to go a lot quicker. Oh, we didn't actually write in our range. I probably should do that real quick. If you take a look from problem number 1, if you take a look back at this problem, in fact, we do have a range that is completely from negative infinity to infinity on different pieces of the graph, of course, but there is no gap because we do have that intercept. And so as we're filling in, and we should have gone back and done that, I apologize, we do have a range that's negative infinity to infinity. Sometimes it's easier to get the whole graph done before identifying that particular piece. Okay, so question 2. So we're doing the same things we were as before. We're identifying all these pieces. So in the first one, we're looking at the domain and range. So for a function like this, right, it's not a rational function. We have a radical function. In particular, we need to remember that we are not allowed to have the denominator, the radicand, the value underneath, be negative. So this needs to be greater than or equal to 0. So everything underneath the radical will be set greater than or equal to 0 and solved. So 2x is greater than or equal to 1. So my value is that x is greater than or equal to 1/2. And if you wanted to put that in interval notation form, it'd be a bracket, 1/2 to infinity. Again, I don't care if you use an interval notation form, but it's possible that WebAssign might force you to. Okay, so the next one is the range. Range is actually really nice for a function like this. It's sort of unfriendly in some fashions for a rational function, but for this one it's really nice. Radicals, when they're given to us in radical form like this, do not have a plus or a minus in front of them. They just don't. This is actually referred to as a principal square root, so we only take the positive part. So what that means is that whatever comes out of this is only positive numbers or 0. So it's very straightforward. We actually have that our range is that the y value is greater than 0, and that's it, greater than or equal to. So as we're doing our range greater than or equal to 0 in interval notation, that would be 0 to infinity. So those go forward really quick. We don't have asymptotes, so there are no asymptotes because it's not a rational function. So there aren't any here, so we don't have to worry about those. We can look at intercepts. So we actually can't let x equal 0, right? So the x-intercept, the y-intercept. The y-intercept is when x is equal to 0, and since x values have to be greater than 1/2, that doesn't happen. So there aren't any. They do not exist, or you can say there are none for the y-intercepts. Your x-intercept, which is when y equals 0, would exist. In particular, we would want to know when what is underneath the radical is equal to 0, because then the square root of 0 is 0. And in particular, that will be at the minimum value that we have for x, which would be 1/2. So my x-intercept would actually be at an x value of 1/2, y value of 0. So in terms of a graph, what pieces do we have so far? Let's draw some of them in. So you notice my graph's a little bit bigger here. I can do that because I have less features, really. So here's my axis. Notice I'm really not giving you much space over here in the quadrants 2, 3, and 4. And that's because my domain and my range told me that I'm really only going to be in quadrant 1, right? My y value has to be positive, my x value has to be bigger than 1/2. And then the last piece of information I just found is that I have an x-intercept over here at 1/2, 0. So that's my first piece to plot. Okay, so I think that took care of all of my pieces from step 2. Oh, no, I didn't. Symmetry. By the same reason as before, we have no symmetry on this graph because we don't have that negative, or that 1/2 showing up as a negative 1/2 as well, which is what we would have if we had either even symmetry, which means it flips over the y-axis, or odd symmetry, which means it flips around the origin. So there's no symmetry. All right, so we're ready for the calculus part. We're ready for the derivative and the second derivative. So the derivative of this is power 1/2, and then I have my 2x minus 1. It would be to the negative 1/2, and then the derivative of the 2x is 2. That's kind of friendly because this 2 and this 2 would cancel, leaving me with 1 over, and it would be, if I was writing it again, this would be 2x minus 1 now in the denominator. Now, the reality is that taking my second derivative, I'm probably going to want to think of it from the middle part there that's highlighted, but that would be my first derivative. So let me leave a little bit of space because we'll be able to set some things equal to 0. I think we have a bit more space on this problem. My second derivative, I would bring my negative 1/2 down. I would have that 2x minus 1, and now to the negative 3/2 times the derivative inside, which is 2. So again, these 2's cancel. I do still have a negative left here, so be a little bit careful on that. And then I would have 1 over, and then this is actually the square root of negative 1 over the square root of it. It's 2x minus 1, but now it's cubed, right? That's that power of 3. Halves gives me the radical. So that's my first derivative, my second derivative. Now, in particular, you'll notice that the first derivative cannot equal 0, right? It can equal does not exist, but it equals does not exist at the same x value that's our minimum x value anyway, at x equal 1/2, right? So while I'm doing a sign chart, my sign chart is sort of very unexciting, at least. I don't want to say unhelpful. It's helpful, but it's just not very exciting. And the reason it's not is because there's only one value on it. It's the value of 1/2. I can't use any of these values, right? Like none of this exists over here because that's not in my domain. I only have one location to test. That is values bigger than 1/2. So we might as well test the value of 1. And if I put the value of 1 in, of course I end up getting a positive number, right? So the graph is increasing. So my graph, I can write it, I'll write it over here. I've got space over here. It's better, just like I did on the last graph. The graph is increasing from 1/2 to infinity. There are no other pieces of the graph. It's an always increasing graph on its domain. Much the same way over here, this cannot equal to 0. But again, it can equal to does not exist. But again, that's at the x equal 1/2. Not very exciting. But I can do a sign chart for it, right? It's 1/2, and none of this exists, just like before. I only have to test one number, and I might as well test the number 1. When I test the number 1, I still get a positive on bottom, but now I get a negative on top. So this one is actually negative, which means it's concave down. So on the entire graph, my entire graph is now concave down. So concave down from 1/2 to infinity. So what does a graph look like that is increasing and concave down? Well, you might think of sort of like a parabola that looks like this. Right? This part is increasing and concave down. The whole thing is concave down, but the first part is increasing. So it's going to have very much that same sort of a feel to it as sort of this left-hand part of this parabola. So my graph has to start at the point I already plotted at 1/2, and it has to be increasing and concave down, and it looks something like this. If you verify that with your calculator, you'll find those pieces as well. Yes, increasing the whole time it's on the domain. Yes, concave down the whole time it's at the domain. It might be worth mentioning, especially if it were to ask you, because WebAssign likes to ask you, what's the max and min? What's the inflection point? Those kinds of things. So there's not one, right? The point of inflection point is that there's none, or it does not exist. My relative extrema, same thing, right? There were none. They don't exist because it's constantly increasing, right? Continually increasing, and point of inflection continually concave down.